5.3 additional properties of the binomial distribution. We will be graphing a binomial distribution. This will be a histogram graph. Each R value is going to be in the middle of the horizontal axis, and your PR value will be on the vertical axis. The example here says create a graph for the binomial distribution when n equals 5. So we're going to go to our table, to n equals 5 on our table, and then go look for our p equals 0.60. So I have my table kind of out of order. So let me go back and get let me go find n equals 5. So it looks like it's right here. We're going to use all of these values right here. So numbers r equals 0 through r equals 5, basically, because those are all the values for n equals 5 from our table. But then we need to go all the way over to 0.60. And that means we are using these values here. These are all the values that represent r equals 0, 1, 2, 3, 4, and 5. So we'll write those down here on the right just so that we have it. So from the n equals 5 section of our binomial probability distribution table, we found that when r equaled 0, the probability of that was 0.010. When r equaled 1, that was 0.077. When r equals 2, that was a 0.230. Remember, these came from the table. Okay, so all these values are from the table. We kind of need them so that we know how to set up our table. Remember, you need to have a title anytime you draw a graph physically, which obviously in your homework you're not doing that. You need to make sure that you remember when you have to draw it or illustrate it, that you give it a title. This one doesn't really tell us what this is about, so I'm just going to put a little star there and put, there's my title. I do know that these are my R values. Remember, like my 0, 1, 2, 3, 4, 5. So we're going to go ahead and do that. 0, 1, 2, 3, 4, 5. If this represented something specific, we would label that. Over here are our P of R values, the probabilities of them. And you're going to need to choose how you want to separate, do your tick marks, I guess. WebAssign is going to choose that for you. So you need to look closely at their scale, what they've separated. So I'll probably go by 0.05s. Like I do that a lot. It works often, not always. Just depends on what your probabilities are. I'll probably just go up to 40 just because my biggest one was 0.346. I probably could have stopped at 0.35, but anyway, so we're going to just go practice graphing that. So remember, it says your R value is in the middle of its bar. So if we said 0.1, that'd be somewhere probably about right here, or 0.01, sorry, it'd be under 0.05. So we know it's somewhere like that. The R value here is 0.07, so that's a little bit before 10. So 0.077. Number 2 is 0.230. Somewhere here. Doesn't have to be perfect. Just get close. 3 is the 0.3, pretty close to 0.35. Oops. That one got crazy. I'm very sorry. 0.346. We'll use that as part of my pattern, I guess, for this next bar, except for it's not gonna be as high. 0.230. It's gonna be here. Oh, 0.259, so actually it needs to be a little bit higher. And 5 is 0.078, so a little bit above 5. Something like that. Probably should look higher than this one, which I didn't do. So all things to maybe think about when you're 0.078, when you're making a graph, how you're separating those. A lot of times in WebAssign, you're going to see colors for your graph. I didn't bring my crayons today, so we're just gonna do some patterns. And this one's pretty little, so we'll just make it solid. So that's all you need to do. Also kind of reviewing those distribution shapes. This one would be a skewed left. So you're always kind of thinking about those distribution shapes, whether they ask you or not. That's just something you'll recognize what's happening with your graph, your histogram. So the mean of a binomial distribution is going to be its expected value. We're going to find that by taking our n times p, so our successes times however many there were. Our standard deviation, we're going to take the square root of n times p times q, so however many there were, times the successes, times the failures. So let's see what that looks like when we do it on the next page. When Taylor shoots field goals in basketball games, the probability he makes a shot is 0.45. So what considers a trial? And in this case, it would be each shot. And really, I can't figure anything else out other than it says a shot is 0.45. Each probability he makes a shot is 0.45. So that would be a success, right? That's what we're calling a success, a make. A failure would be a miss. And I could figure out my failures by taking 1 minus that. But I really can't figure my in part until I read the next little section, because it says out of 6 shots. Then we could fill in our n equals. What is expected? What is the expected number of goals Taylor will make? So we're going to say our n times our p value. So our n value is 6 times my p value is 0.45. And so I would end up getting 2.7. If I were to explain that, this is representing the number of shots. So you can't make a part of a shot, but we could say somewhere between 2 and 3 shots, right? So I expect Taylor to make 2 to 3 shots. What is the standard deviation? So this is where our standard deviation is taking the square root of n times p times q. So our n value is 6, our p value is 0.45, and our q value is 0.55. So you'll type that into your calculator. You can do it just like that. The square root of 6 times 0.45 times 0.55 is 1.218, and then it goes on and on. A lot of times you'll be rounding to 2 digits in this section, so we would say 1.22. So what would that mean? How does that standard deviation apply? So we could say if we rounded to 1, that Taylor could make maybe 1 less. So Taylor could make 1 to 4 shots, 1 less and 1 more. If I rounded to a whole shot, I would maybe, like I said, just round down. Just normal rounding rules. So that's what standard deviation does. It kind of gives a bigger range of what could happen in real life. The next example, in a pharmaceutical trial, 60% of the men tested remained bald after using Rogaine. The cream will be tested on 5 men who have male pattern baldness. How many men do you expect to remain bald? So this one's kind of weird because you would think remaining bald was a success, but our statistic that they give us refers to remaining bald. So actually that's going to be our success. So our trial, we're trialing each men. So each man that was men in the trial. Success would be being bald. Remaining bald. Maybe I should have written remain first. And then the failure would be not bald. Maybe they start growing hair. You would think if they're doing a pharmaceutical trial that maybe they would want to grow hair if they're using Rogaine, right? So it's a flip side. You need to make sure you're paying attention to what the statistic they give you, and they're calling that a success in this case. And they tell us we did 5 men. Our success was 60% remained bald, so that means 40% grew hair. So we are going to go find, it says, how many men do you expect to remain bald? And so that's the terminology you're going to be looking for. So in statistics, you've probably recognized, you have to look for some keywords, and expect, the word expect to is a big part. And that means you're going to be working with your, I just did it backwards, your mean of your N times P power. That's going to be the expected value. That's the formula we use. So my mean in this case is 5 times 0.60. And so when you multiply that, that's going to be the number 3. So 3 men, I would expect 3 men to remain bald. Three out of the 5. Example, a dealer considers a car to be successful if it doesn't require repairs covered by the warranty. If the probability of a car being successful is 80%, find the mean and standard deviation for the number of successful cars among 3 cars sold in one day. So each time you need to think, I am talking about each car. You need to think, what is this trial about? Identify what a success means. This meant there were no repairs. They didn't ever go back to the repair shop. A failure would mean at some point it had to have repairs, needed repairs. So this says how many? There were 3 cars sold in a day. It said if the probability of a car being successful is 80%, that means 80% of them never needed repairs, then that means 20% did. So if we're finding that, we have to find the mean. Sometimes it just straight out tells you like this in the word, and sometimes it'll say expect to when we just have to find the mean. So our mean is by taking N times P, so 3 times 0.8. And so you would get 2.4. Our standard deviation is by taking, I guess I should have used the symbol. Our standard deviation is that sigma symbol with our N times P times Q. So we're taking 3 times 0.8 times 0.2 underneath that radical. So the square root of 3 times 0.8 times 0.2 is, if we rounded to 2 digits, we'd call that 0.69. So what would that mean if we explained those things? I would expect, if we just rounded down, but it would be between 2 and 3 cars to not need repairs. 2 to 3 cars would not need repairs out of the 3. What would this mean? We could be one less or one more, but we're only doing 3 cars sold in a day. So if we did one less, we would say, applying the standard deviation, 1 to 3 cars would not need repairs. Because it's still about what would not be. So one more in there ended up needing repairs if you applied the standard deviation. So let's recall Chevy Chevs. Remember there was, like say you had a number line here and our mean is always kind of like in the middle of our table value. So Chevy Chevs tells us that no matter what the distribution looks like, at least 75% of the data should fall within 2 standard deviations. So these 2 hash marks would represent 1, and this would be like saying 2 standard deviations. And what this means, and you may have, 3 standard deviations, 4, each hash mark could represent a standard deviation. So what that means is all the data falls within here. These would be called out here outliers, things that are outside of 2 standard deviations. So for a binomial distribution, it is considered unusual for the number of successes to be outside of that, basically lower than minus 2.5, 2.5 standard deviations, and plus 2.5 standard deviations. So we're going to apply what that means. In this example, it says consider a binomial experiment with 20 trials where p equals 0.7. The expected number of successes is 14. With a standard deviation of 2, what number of successes would be considered unusual? So this is how you know you're going to be doing this next step with it. In the terminology that'll pop out will say considered unusual. Also, expected number of successes means that you're working with your mean. So expected, remember you're working with that. That's a good indication that you're working with your mean. So our N number, we said there were 20 trials. Our successes was 0.70. So we already know our successes. Our mean, they tell us, is 14. So we don't have to go find it. And our standard deviation they give to you is 2. And so you're really just doing the lower than and less than. So the lower than portion is you're taking that mean and you're subtracting 2.5 standard deviations. So my mean is 14 minus 2.5 times my standard deviation of 2. So when you calculate that, you're going to get the number 9. Okay, if I'm working with the higher than portion, this would just have a plus sign between those 2 things. I know my little symbol looks like a 6, but this is standard deviation symbol. That's a sigma symbol. Okay, don't let that confuse you. You can put it in a parentheses if you need to, so it doesn't look like it's the number 6. Okay, so 14 plus 2.5 times 2. This time you're adding it, so you'll get 19. So what that means is if you have a graph, and we're going to start doing this more often, your mean is 14, so it's right there in the middle. That's your mean. You can go up by 2s, or at least I would, since the standard deviation is 2. That's what you need to do, I suppose. And you can take this as far as you want. So I'm going to take it to between 6 and 22. So if this is my mean, this would be 1 standard deviation. This would be 2. And right here is our half. So that would be where 19 falls. This would be 1 standard deviation. This would be 2. And then right there in the middle would be our half, which would be 9. So what this means is the data falls between, and I'll put these numbers down here, the lower limit, which was 9, and the upper limit, which is 18. So they fall somewhere between those digits on the number line. Any other value out here, they're considered outliers, things that could skew 75% of the data.